So what about when Nolan woke up? Well, do you remember a moment where he was able to not move the cursor, but get signal from the brain such that it was able to show that there's a connection?
Yeah. Yeah. So we are quite excited to move as quickly as we can. And Noland was really, really excited to get started. He wanted to get started actually the day of surgery. But we waited till the next morning very patiently. It's a long night. And the next morning in the ICU where he was recovering, he wanted to get started and actually start to understand what kind of signal we can measure from his brain. And maybe for folks who are not familiar with the Neuralink system, we implant the Neuralink system or the Neuralink implant in the motor cortex. So the motor cortex is responsible for representing things like motor intent. So if you imagine closing and opening your hand, that kind of signal representation would be present in the motor cortex. If you imagine moving your arm back and forth or wiggling a pinky, this sort of signal can be present in the motor cortex. So one of the ways we start to sort of map out what kind of signal do we actually have access to in any particular individual's brain is through this task called body mapping. And body mapping is where you essentially present a visual to the user and you say, hey, imagine doing this. And the visual is, a 3D hand opening and closing or index finger modulating up and down. And you ask the user to imagine that. And obviously you can't see them do this because they're paralyzed. So you can't see them actually move their arm. But while they do this task, you can record neural activity. And you can basically offline model and check, can I predict or can I detect the modulation corresponding with those different actions? And so we did that task and we realized, hey, there's actually some modulation associated with some of his hand motion, which was the first indication that, okay, we can potentially use that modulation to do useful things in the world. For example, control a computer cursor. And he started playing with it, the first time we showed him it. And we actually just took the same live view of his brain activity and put it in front of him. And we said, hey, you tell us what's going on. Mm-hmm. We're not you. You're able to imagine different things. And we know that it's modulating some of these neurons. So you figure out for us what that is actually representing. And so he played with it for a bit. He was like, I don't quite get it yet. He played for a bit longer. And he said, oh, when I move this finger, I see this particular neuron start to fire more. And I said, okay, prove it. Do it again. And so he said, okay, 3, 2, 1, boom. Mm-hmm. And the minute he moved, you can see like instantaneously, this neuron is firing. Single neuron, I can tell you the exact channel number if you're interested. It's stuck in my brain now forever. But that single channel firing was a beautiful indication that it was behaviorally modulated neural activity that could then be used for downstream tasks like decoding a computer cursor.
And when you say single channel, is that associated with a single electrode?
Yeah, so channel and electrode are interchangeable.
And there's 1,024 of those.
1,024, yeah.
It's incredible that works. That really, when I was learning about all this and like loading it in, it was just blowing my mind that the intention, you can visualize yourself moving the finger, that can turn into a signal. And the fact that you can then skip that step and visualize the cursor moving or have the intention of the cursor moving and that leading to a signal that can then be used to move the cursor. There is so many exciting things there to learn about the brain, about the way the brain works. The very fact of their existing signal that can be used is really powerful.
Yep.
But it feels like that's just like the beginning of figuring out how that signal can be used really, really effectively. I should also just, there's so many fascinating details here, but you mentioned the body mapping step. At least in the version I saw that Noland was showing off, there's like a super nice interface, like a graphical interface. Yeah. Like, it just felt like I was like in the future because it like, I guess it visualizes you moving the hand. Yep. And there's a very like a sexy polished interface that hello. Yeah. I don't know if there's a voice component, but it just felt like it's like when you wake up in a really nice video game and this is a tutorial at the beginning of that video game. Yeah. This is what you're supposed to do. It's cool.
No, I mean, the future should feel like the future.
But it's not easy to pull that off. I mean, it needs to be simple, but not too simple.
Yeah, and I think the UX design component here is underrated for BCI development in general. There's a whole interaction effect between the ways in which you visualize an instruction to the user and the kinds of signal you can get back. And that quality of sort of your behavioral alignment to the neural signal is a function of how good you are at expressing to the user what you want them to do. And so, yeah, we spend a lot of time thinking about the UX, of how we build our applications, of how the decoder actually functions, the control surfaces it provides to the user. All these little details matter a lot.
So maybe it'd be nice to get into a little bit more detail of what the signal looks like and what the decoding looks like. Yeah. So there's N1 implant that has, like we mentioned, 1,024 electrodes, and that's collecting raw data, raw signal. What does that signal look like? And what are the different steps along the way before it's transmitted, and what is transmitted, all that kind of stuff.
Yeah. This is going to be a fun one.
Let's go.
Maybe before diving into what we do, it's worth understanding what we're trying to measure, because that dictates a lot of the requirements for the system that we build. And what we're trying to measure is really individual neurons producing action potentials. And action potential is, you can think of it like a little electrical impulse that you can detect if you're close enough. And by being close enough, I mean like within, let's say, 100 microns of that cell. And 100 microns is a very, very tiny distance. And so the number of neurons that you're going to pick up with any given electrode is just a small radius around that electrode.
Mm-hmm.
And the other thing worth understanding about the underlying biology here is that when neurons produce an action potential, the width of that action potential is about 1 millisecond. So from the start of the spike to the end of the spike, that whole width of that sort of characteristic feature of a neuron firing is 1 millisecond wide. And if you want to detect that an individual spike is occurring or not, you need to sample that signal or sample the local field potential nearby that neuron much more frequently than once a millisecond. You need to sample many, many times per millisecond to be able to detect that this is actually the characteristic waveform of a neuron producing an action potential.
Mm-hmm.
And so we sample across all 1,024 electrodes about 20,000 times a second. 20,000 times a second means for every given 1 millisecond window, we have about 20 samples that tell us what that exact shape of that action potential looks like.
Mm-hmm.
And once we've sort of sampled at super high rate the underlying electrical field nearby these cells, we can process that signal into just where do we detect a spike or where do we not? Sort of a binary signal, 1 or 0. Do we detect a spike in this 1 millisecond or not? And we do that because the actual information carrying sort of subspace of neural activity is just when are spikes occurring.
Mm-hmm.
Essentially, everything that we care about for decoding can be captured or represented in the frequency characteristics of spike trains, meaning how often are spikes firing in any given window of time. And so that allows us to do sort of a crazy amount of compression from this very rich, high density, signal to something that's much, much more sparse and compressible that can be sent out over a wireless radio, like a Bluetooth communication, for example.
Quick tangents here. You mentioned electrode, neuron. There's a local neighborhood of neurons nearby. How difficult is it to isolate from where the spike came from?
Yeah, so there's a whole field of sort of academic neuroscience work on exactly this problem of basically given a single electrode or given a set of electrodes measuring a set of neurons, how can you sort of spike sort
Mm-hmm.
which spikes are coming from what neuron? And this is a problem that's pursued in academic work because you care about it for understanding what's going on in the underlying sort of neuroscience of the brain. If you care about understanding how the brain's representing information, how that's evolving through time, then that's a very, very important question to understand. For sort of the engineering side of things, at least at the current scale, if the number of neurons per electrode is relatively small, you can get away with basically ignoring that problem completely. You can think of it like sort of a random projection of neurons to electrodes. And there may be, in some cases, more than one neuron per electrode. But if that number is small enough, those signals can be thought of as sort of a union of the two.
Mm-hmm.
And for many applications, that's a totally reasonable trade-off to make and can simplify the problem a lot. And as you sort of scale out channel count, the relevance of distinguishing individual neurons becomes less important because you have more overall signal and you can start to rely on sort of correlations or covariance structure in the data to help understand when that channel is firing, what does that actually represent? Because you know that when that channel is firing in concert with these other 50 channels, that means move left. But when that same channel is firing with concert with these other 10 channels, that means move right.
Okay, so you have to do this kind of spike detection on board. And you have to do that super efficiently, so fast and not use too much power because you don't want to be generating too much heat. So it have to be a super simple signal processing step.
Yeah.
Is there some wisdom you can share about what it takes to overcome that challenge?
Yeah. So we've tried many different versions of basically turning this raw signal into sort of a feature that you might want to send off the device. And I'll say that I don't think we're at the final step of this process. This is a long journey. We have something that works clearly today, but there can be many approaches that we find in the future that are much better than what we do right now. So some versions of what we do right now, and there's a lot of academic heritage to these ideas. So I don't want to claim that these are original Neuralink ideas or anything like that. But one of these ideas is basically to build a sort of like a convolutional filter almost, if you will, that slides across the signal and looks for a certain template to be matched. And that template consists of sort of how deep the spike modulates, how much it recovers, and what the duration and window of time is that the whole process takes. And if you can see in the signal that that template is matched within certain bounds, then you can say, okay, that's a spike. One reason that approach is super convenient is that you can actually implement that extremely efficiently in hardware, which means that you can run it in low power across 1,024 channels all at once. Another approach that we've recently started exploring, and this can be combined with the spike detection approach, is something called spike band power. And the benefits of that approach are that you may be able to pick up some signal from neurons that are maybe too far away to be detected as a spike, because the farther away you are from an electrode, the weaker that actual spike waveform will look like on that electrode. So you might be able to pick up population level activity of things that are, maybe slightly outside the normal recording radius, what neuroscientists sometimes refer to as the hash of activity, the other stuff that's going on.
Yeah.
And you can look at sort of across many channels how that sort of background noise is behaving, and you might be able to get more juice out of the signal that way. But it comes at a cost. That signal is now a floating point representation, which means it's more expensive to send out over a power. It means you have to find different ways to compress it that are different than what you can apply to binary signals. So there's a lot of different challenges associated with these different modalities.
So also in terms of communication, you're limited by the amount of data you can send.
Yeah.
So, and also because you're currently using the Bluetooth protocol, you have to batch stuff together. But you have to also do this keeping the latency crazy low, like crazy low. Anything to say about the latency?
Yeah, this is a passion project of mine. So I want to build the best mouse in the world.
Yeah.
I don't want to build like the Chevrolet Spark or whatever of electric cars. I want to build like the Tesla Roadster version of a mouse. And I really do think it's quite possible that within 5 to 10 years that most esports competitions are dominated by people with paralysis. This is like a very real possibility for a number of reasons. One is that they'll have access to the best technology to play video games effectively. The second is they have the time to do so. So those two factors together are particularly potent for esport competitors.
Unless people without paralysis are also allowed to implant Neuralink,
right?
Which is another way to interact with a digital device. Mm-hmm. And there's something to that. If it's a fundamentally different experience, more efficient experience, even if it's not like some kind of full-on high bandwidth communication, if it's just the ability to move the mouse 10x faster, like the bits per second, if I can achieve a bits per second at 10x what I can do with the mouse, that's a really interesting possibility of what that can do, especially as you get really good at it with training.
It's definitely the case that you have a higher ceiling of performance, because you don't have to buffer your intention through your arm, through your muscle. You get, just by nature of having a brain implant at all, like 75 millisecond lead time on any action that you're actually trying to take. And there's some nuance to this, like there's evidence that the motor cortex, you can sort of plan out sequences of action, so you may not get that whole benefit all the time. But for sort of like reaction time style games where you just want to, somebody's over here, snipe them, that kind of thing, you actually do have just an inherent advantage because you don't need to go through muscle. So the question is just how much faster can you make it? And we're already, faster than, what you would do if you're going through muscle from a latency point of view. And we're in the early stages of that. I think we can push it. Sort of our end-to-end latency right now from brain spike to cursor movement is about 22 milliseconds. If you think about the best mice in the world, the best gaming mice, that's about 5 milliseconds-ish of latency, depending on how you measure, depending how fast your screen refreshes. There's a lot of characteristics that matter there. But yeah, and the rough time for like a neuron in the brain to actually impact your command of your hand is about 75 milliseconds. So if you look at those numbers, you can see that we're already competitive and slightly faster than what you'd get by actually moving your hand. And this is something that, if you ask Noland about it, when he moved the cursor for the first time, we asked him about this. It was something I was super curious about. Like, what does it feel like when you're modulating, a click intention, or when you're trying to just move the cursor to the right? He said it moves before he is like actually intending it to, which is kind of a surreal thing and something that, I would love to experience myself one day. What is that like to have the thing just be so immediate, so fluid that it feels like it's happening before you're actually intending it to move?
Yeah, I suppose we've gotten used to that latency, that natural latency that happens. So Is currently the bottleneck the communication? So like the Bluetooth communication? What's the actual bottleneck? I mean, there's always going to be a bottleneck, but what's the current bottleneck?
Yeah, a couple things. So kind of hilariously, Bluetooth low energy protocol has some restrictions on how fast you can communicate. So the protocol itself establishes a standard of, the most frequent sort of updates you can send are on the order of 7.5 milliseconds. And as we push latency down to the level of sort of individual spikes impacting control, that level of resolution, that kind of protocol is going to become a limiting factor at some scale. Another sort of important nuance to this is that it's not just the Neuralink itself that's part of this equation. If you start pushing latency sort of below the level of how fast screens refresh, then you have another problem. Like you need your whole system to be able to be as reactive as the sort of limits of what the technology can offer.
Yes.
Like you need the screen, like 120 hertz just doesn't, work anymore if you're trying to have something respond at something that's, at the level of 1 millisecond.
That's a really cool challenge. I also like that for a t-shirt, the best mouse in the world. Tell me on the receiving end, so the decoding step. Now we figured out what the spikes are. We got them all together. Now we're sending that over to the app. What's the decoding step look like?
Yeah. So maybe first, what is decoding? I think there's probably a lot of folks listening that just have no clue what it means to decode brain activity.
Actually, even if we zoom out beyond that, what is the app? So there's an implant that's wirelessly communicating with any digital device that has an app installed.
Yep.
So maybe can you tell me at high level what the app is, what the software is outside of the brain?
Yeah. So maybe working backwards from the goal. The goal is to help someone with paralysis, in this case, Noland, be able to navigate his computer independently. And we think the best way to do that is to offer them the same tools that we have to navigate our software, because we don't want to have to rebuild an entire software ecosystem for the brain, at least not yet. Maybe someday you can imagine there's UXs that are built natively for BCI, but in terms of what's useful for people today, I think most people would prefer to be able to just control mouse and keyboard inputs to all the applications that they want to use for their daily jobs, for communicating with their friends, etc. And so the job of the application is really to translate this wireless stream of brain data coming off the implant into control of the computer. And we do that by essentially building a mapping from brain activity to sort of the HID inputs to the actual hardware. So HID is just the protocol for communicating like input device events. So for example, move mouse to this position or press this key down. And so that mapping is fundamentally what the app is responsible for. But there's a lot of nuance of how that mapping works that we spent a lot of time to try to get right. And we're still in the early stages of a long journey to figure out how to do that optimally. So one part of that process is decoding. So decoding is this process of taking the statistical patterns of brain data that's being channeled across this Bluetooth connection to the application and turning it into, for example, a mouse movement. And that decoding step, you can think of it in a couple different parts. So similar to any machine learning problem, there's a training step and there's an inference step. The training step in our case is a very intricate behavioral process where the user has to imagine doing different actions. So for example, they'll be presented a screen with a cursor on it, and they'll be asked to push that cursor to the right. Then imagine pushing that cursor to the left, push it up, push it down. And we can basically build up a pattern, or using any sort of modern ML method, a mapping of given this brain data and that imagined behavior, map one to the other. And then at test time, you take that same pattern matching system, in our case, it's a deep neural network, and you run it, and you take the live stream of brain data coming off their implant, you decode it by pattern matching to what you saw at calibration time, and you use that for control of the computer. Now, a couple like sort of rabbit holes that I think are quite interesting. One of them has to do with how you build that best template matching system, because there's a variety of behavioral challenges and also debugging challenges when you're working with someone who's paralyzed. Because again, fundamentally, you don't observe what they're trying to do. You can't see them attempt to move their hand. And so you have to figure out a way to instruct the user to do something and validate that they're doing it correctly, such that then you can downstream build with confidence the mapping between the neural spikes and the intended action. And by doing the action correctly, what I really mean is at the level of resolution of what neurons are doing. So if in an ideal world, you could get a signal of behavioral intent that is ground truth accurate at the scale of sort of 1 millisecond resolution, then with high confidence, I could build a mapping from my neural spikes to that behavioral intention. But the challenge is, again, that you don't observe what they're actually doing. And so there's a lot of nuance to how you build user experiences that give you more than just sort of a coarse, on average, correct representation of what the user's intending to do. If you want to build the world's best mouse, you really want it to be as responsive as possible. You want it to be able to do exactly what the user is intending at every sort of step along the way, not just on average be correct when you're trying to move it from left to right. And building a behavioral sort of calibration game or sort of software experience that gives you that level of resolution is what we spend a lot of time working on.
So the calibration process, the interface, has to encourage precision. Meaning, like, whatever it does, it should be super intuitive, that the next thing the human is going to likely do is exactly that intention that you need, and only that intention.
Yeah.
And you don't have any feedback except that may be speaking to you afterwards, what they actually did. You can't, oh yeah.
Right.
So that's fundamentally, that is a really exciting UX challenge, because that's all on the UX. It's not just about being friendly or nice or usable.
Yeah.
It's like
user experience is how it works.
It's how it works.
Yeah.
For the calibration, and calibration, at least at this stage of Neuralink, is like fundamental to the operation of the thing. And not just calibration, but continued calibration, essentially.
Yeah. And maybe you said something that I think is worth exploring there a little bit. You said it's, primarily a UX challenge. And I think a large component of it is, but there is also a very interesting machine learning challenge here, which is given some, data set, including some on average correct behavior of asking the user to move up or move down, move right, move left. And given a data set of neural spikes, is there a way to infer in some kind of semi-supervised or entirely unsupervised way what that high resolution version of their intention is? And if you think about it, like, there probably is, because there are enough data points in the data set, enough constraints on your model, that there should be a way with the right sort of formulation to let the model figure out itself. For example, at this millisecond, this is exactly how hard they're pushing upwards. And at this millisecond, this is how hard they're trying to push upwards.
It's really important to have very clean labels. Yes. So, like, the problem becomes much harder from the machine learning perspective if the labels are noisy.
That's correct.
And then to get the clean labels, that's a UX challenge.
Correct. Although clean labels, I think maybe it's worth exploring what that exactly means. I think any given labeling strategy will have some number of assumptions it makes about what the user is attempting to do. Those assumptions can be formulated in a loss function, or they can be formulated in terms of heuristics that you might use to just try to estimate or guesstimate what the user is trying to do. And what really matters is how accurate are those assumptions. For example, you might say, hey, user, push upwards and follow the speed of this cursor. And your heuristic might be that they're trying to do it exactly what that cursor is trying to do. Another competing heuristic might be they're actually trying to go slightly faster at the beginning of the movement and slightly slower at the end. And those competing heuristics may or may not be accurate reflections of what the user is trying to do. Another version of the task might be, hey, user, imagine moving this cursor a fixed offset. So rather than follow the cursor, just try to move it exactly 200 pixels to the right. So here's the cursor, here's the target. Okay, cursor disappears. Try to move that now invisible cursor 200 pixels to the right. And the assumption in that case would be that the user can actually modulate correctly that position offset. But that position offset assumption might be a weaker assumption, and therefore potentially you can make it more accurate than these heuristics that are trying to guesstimate at each millisecond what the user is trying to do. So you can imagine different tasks that make different assumptions about the nature of the user intention, and those assumptions being correct is what I would think of as a clean label.
For that step, what are we supposed to be visualizing? There's a cursor, and you want to move that cursor to the right, the left, the up and down, or maybe move them by a certain offset. So that's one way. Is that the best way to do calibration? So, for example, an alternative crazy way that probably is playing a role here is a game like WebGrid, where you're just getting a very large amount of data, the person playing a game, where if they're in a state of flow, maybe you can get clean signal as a side effect.
Yep.
Is that not an effective way for initial calibration?
Yeah, great question. There's a lot to unpack there. So the first thing I would draw a distinction between is sort of open loop versus closed loop. So open loop, what I mean by that is the user is sort of going from 0 to 1. They have no model at all, and they're trying to get to the place where they have some level of control at all. In that setup, you really need to have some task that gives the user a hint of what you want them to do, such that you can build this mapping again from brain data to output. Then once they have a model, you could imagine them using that model and actually adapting to it and figuring out the right way to use it themselves, and then retraining on that data to give you sort of a boost in performance. There's a lot of challenges associated with both of these techniques, and we can sort of rabbit hole into both of them if you're interested. But the sort of challenge with the open loop task is that the user themselves doesn't get proprioceptive feedback about what they're doing. They don't, necessarily perceive themselves or feel, the mouse under their hand when they're using an open loop, or when they're trying to do an open loop calibration. They're being asked to perform something like, imagine if you sort of had your whole right arm numbed and you stuck it in a box and you couldn't see it. So you had no visual feedback and you had no proprioceptive feedback about what the position or activity of your arm was. And now you're asked, okay, given this thing on the screen that's moving from left to right, match that speed. And you basically can try your best to, invoke whatever that imagined action is in your brain that's moving the cursor from left to right. But in any situation, you're going to be inaccurate and maybe inconsistent in how you do that task. And so that's sort of the fundamental challenge of open loop. The challenge with closed loop is that once the user's given a model and they're able to start moving the mouse on their own, they're going to very naturally adapt to that model. And that co-adaptation between the model learning what they're doing and the user learning how to use the model may not find you the best sort of global minima. It may be that your first model was noisy in some ways, or maybe just had some quirk. There's some part of the data distribution it didn't cover super well. And the user now figures out, because they're a brilliant user like Noland, they figure out the right sequence of imagined motions or the right angle they have to hold their hand at to get it to work. And they'll get it to work great. But then the next day they come back to their device and maybe they don't remember exactly all the tricks that they used the previous day. And so there's a complicated sort of feedback cycle here that can emerge and can make it a very, very difficult debugging process.
Okay, there's a lot of really fascinating things there. Actually, just to stay on the closed loop, I've seen situations. This actually happened watching psychology grad students. They use a piece of software when they don't know how to program themselves. They use a piece of software that somebody else wrote, and it has a bunch of bugs. And they figure out and they've been using it for years.
Yeah.
They figure out ways to work around it.
Yeah.
Oh, that just happens. Nobody considers maybe we should fix this. They just adapt. And that's a really interesting notion that we're really good at adapting, but you need to still, that might not be the optimal.
Yeah.
Okay, so how do you solve that problem? Do you have to restart from scratch every once in a while kind of thing?
Yeah, it's a good question. First and foremost, I would say this is not a solved problem. And for anyone who's listening in academia who works on BCIs, I would also say this is not a problem that's solved by simply scaling channel count. So this is, maybe that can help, and you can get sort of richer covariance structures that you can use to exploit when trying to come up with good labeling strategies. But if you're interested in problems that aren't going to be solved inherently by just scaling channel count, this is one of them. Mm-hmm. Yeah, so how do you solve it? It's not a solved problem. That's the first thing I want to make sure it gets across. The second thing is any solution that involves closed loop is going to become a very difficult debugging problem. And one of my sort of general heuristics for choosing what problems to tackle is that you want to choose the one that's going to be the easiest to debug. Because if you can do that, even if the ceiling is lower, you're going to be able to move faster because you have a tighter iteration loop debugging the problem. And in the open loop setting, there's not a feedback cycle to debug with the user in the loop. And so there's some reason to think that that should be an easier debugging problem. The other thing that's worth understanding is that even in a closed loop setting, there's no special sauce or magic of how to infer what the user is truly attempting to do. In the closed loop setting, although they're moving the cursor on the screen, they may be attempting something different than what your model is outputting. So what the model is outputting is not a signal that you can use to retrain if you want to be able to improve the model further. You still have this very complicated guesstimation or unsupervised problem of figuring out what is the true user intention underlying that signal. And so the open loop problem has the nice property of being easy to debug, and the second nice property of it has all the same information and content as the closed loop scenario. Another thing I want to mention and call out is that this problem doesn't need to be solved in order to give useful control to people. Even today with the solutions we have now and that academia has built up over decades, the level of control that can be given to a user, today is quite useful. It doesn't need to be solved to get to that level of control. But again, I want to build the world's best mouse. I want to make it, so good that it's not even a question that you want it. And to build the world's best mouse, the superhuman version, you really need to nail that problem. And a couple maybe details of previous studies that we've done internally that I think are very interesting to understand when thinking about how to solve this problem. The first is that even when you have ground truth data of what the user is trying to do, and you can get this with an able-bodied monkey, a monkey that has a Neuralink device implanted and moving a mouse to control a computer, even with that ground truth data set, it turns out that the optimal thing to predict to produce high-performance BCI is not just the direct control of the mouse. You could imagine, building a data set of what's going on in the brain and what is the mouse exactly doing on the table. And it turns out that if you build the mapping from neural spikes to predict exactly what the mouse is doing, that model will perform worse than a model that is trained to predict sort of higher level assumptions about what the user might be trying to do. For example, assuming that the monkey is trying to go in a straight line to the target.
Mm-hmm.
It turns out that making those assumptions is actually more effective in producing a model than actually predicting the underlying hand movement.
So the intention, not the physical movement or whatever.
Yeah.
There's obviously a really strong correlation between the two, but the intention is a more powerful thing to be chasing.
Right.
Well, that's also super interesting. I mean, the intention itself is fascinating because, yes, with the BCI here in this case, with the digital telepathy, you're acting on the intention, not the action, which is why there's an experience of like feeling like it's happening before you meant for it to happen. That is so cool. And that is why you could achieve like superhuman performance probably in terms of the control of the mouse. So for open loop, just to clarify, so whenever the person is tasked to like move the mouse to the right, you said there's not feedback. So they don't get that satisfaction of like actually getting it to move, right?
So you could imagine giving the user feedback on a screen, but it's difficult because at this point you don't know what they're attempting to do. So what can you show them that would basically give them a signal of I'm doing this correctly or not correctly? So let's take a very specific example. Like maybe your calibration task looks like you're trying to move the cursor a certain position offset. So your instructions to the user are, hey, the cursor's here. Now, when the cursor disappears, imagine moving it 200 pixels from where it was to the right to be over this target. In that kind of scenario, you could imagine coming up with some sort of consistency metric that you could display to the user of, okay, I know what the spike train looks like on average when you do this action to the right. Maybe I can produce some sort of probabilistic estimate of how likely is that to be the action you took given the latest trial or trajectory that you imagined. And that could give the user some sort of feedback of how consistent are they across different trials. You could also imagine that if the user is prompted with that kind of consistency metric, that maybe they just become more behaviorally engaged to begin with because the task is kind of boring when you don't have any feedback at all. And so there may be benefits to the user experience of showing something on the screen, even if it's not accurate, just because it keeps the user motivated to try to increase that number or push it upwards.
So there's a psychology element here.
Yeah, absolutely.
And again, all of that is UX challenge. How much signal drift is there? Hour to hour, day to day, week to week, month to month? How often do you have to recalibrate because of the signal drift?
Yeah. So this is a problem we've worked on both with NHP, non-human primates, before our clinical trial, and then also with Noland during the clinical trial. Maybe the first thing that's worth stating is what the goal is here. So the goal is really to enable the user to have a plug-and-play experience where, I guess they don't have to plug anything in, but a play experience where they can use the device whenever they want to, however they want to. Mm-hmm. And that's really what we're aiming for. And so there can be a set of solutions that get to that state without considering this non-stationarity problem. So maybe the first solution here that's important is that they can recalibrate whenever they want. This is something that that Noland has the ability to do today. So he can recalibrate the system, at 2 a.m. in the middle of the night without his, caretaker or parents or friends around to help push a button for him. The other important part of the solution is that when you have a good model calibrated, that you can continue using that without needing to recalibrate it. So how often he has to do this recalibration today depends really on his appetite for performance. There are, we observe a sort of a degradation through time of how well any individual model works, but this can be mitigated behaviorally by the user adapting their control strategy. It can also be mitigated through a combination of sort of software features that we provide to the user. For example, we let the user adjust exactly how fast the cursor is moving. We call that the gain, for example, the gain of how fast the cursor reacts to any given input intention. They can also adjust the smoothing, how smooth the output of that cursor intention actually is. They can also adjust the friction, which is how easy is it to stop and hold still. And all these software tools allow the user a great deal of flexibility and troubleshooting mechanisms to be able to solve this problem for themselves.
By the way, all of this is done by looking to the right side of the screen, selecting the mixer, and in the mixer you have it's
like DJ mode. DJ mode for your BCI.
So I mean, it's a really well done interface. It's really, really well done. And so yeah, there's that bias that there's a cursor drift that Noland talked about in a stream. Although he said that you guys were just playing around with it with him and they're constantly improving. So that could have been just a snapshot of that particular moment, a particular day. But he said that there was this cursor drift and this bias that could be removed by him, I guess, looking to the right side of the screen, the left side of the screen to kind of adjust the bias.
Yeah.
That's one interface action, I guess, to adjust the bias.
Yeah. So this is actually an idea that comes out of academia. There is some prior work with sort of brain gate clinical trial participants where they pioneered this idea of bias correction. The way we've done it, I think, is it's very productized, very beautiful user experience where the user can essentially flash the cursor over to the side of the screen, and it opens up a window where they can actually sort of adjust or tune exactly the bias of the cursor. So bias, maybe for people who aren't familiar, is just sort of what is the default motion of the cursor if you're imagining nothing. Mm-hmm. And it turns out that that's one of the first sort of qualia of the cursor control experience that's impacted by neural non-stationarity.
Qualia of the cursor experience.
I don't know how else to describe it. Like, I'm not the guy moving.
Very poetic. I love it. The qualia of the cursor experience. Yeah, I mean, it sounds poetic, but it is deeply true. There is an experience when it works well. It is a joyful, a really pleasant experience, and when it doesn't work well, it's a very frustrating experience. That's actually the art of UX. It's like you have the possibility to frustrate people or the possibility to give them joy.
And at the end of the day, it really is truly the case that UX is how the thing works. And so it's not just like what's showing on the screen. It's also, what control surfaces does a decoder provide the user? Like we want them to feel like they're in the F1 car, not like the, some like minivan, right? And that really truly is how we think about it. Noland himself is an F1 fan. So we refer to ourselves as a pit crew. He really is truly the F1 driver. And there's different, control surfaces that different kinds of cars and airplanes provide the user. And we take a lot of inspiration from that when designing how the cursor should behave. And maybe one nuance of this is, even details like when you move a mouse on a MacBook trackpad, the sort of response curve of how that input that you give the trackpad translates to cursor movement is different than how it works with a mouse. Mm-hmm. When you move on the trackpad, there's a different response function, a different curve to how much a movement translates to input to the computer than when you do it physically with a mouse. And that's because somebody sat down a long time ago when they're designing the initial input systems to any computer, and they thought through exactly how it feels to use these different systems. And now we're designing sort of the next generation of this input system to a computer, which is entirely done via the brain. And there's no proprioceptive feedback. Again, you don't feel the mouse in your hand. You don't feel the keys under your fingertips. And you want a control surface that still makes it easy and intuitive for the user to understand the state of the system and how to achieve what they want to achieve. And ultimately, the end goal is that UX is completely, it fades into the background. It becomes something that's so natural and intuitive that it's subconscious to the user. And they just should feel like they have basically direct control over the cursor. It just does what they want it to do. They're not thinking about the implementation of how to make it do what they want it to do. It's just doing what they want it to do.
Is there some kind of things along the lines of like Fitz law where you should move the mouse in a certain kind of way that maximizes your chance to hit the target? I don't even know what I'm asking, but I'm hoping the intention of my question will land on a profound answer. No. Is there some kind of understanding of the laws of UX when it comes to the context of somebody using their brain to control it? Like that's different than actual with a mouse.
I think we're in the early stages of discovering those laws. So I wouldn't claim to have solved that problem yet. But there's definitely some things we've learned that make it easier for the user to get stuff done. Mm-hmm. And it's pretty straightforward when you verbalize it, but it takes a while to actually get to that point when you're in the process of debugging this stuff in the trenches. One of those things is that any machine learning system you build has some number of errors. And it matters how those errors translate to the downstream user experience. For example, if you're developing a search algorithm in your photos, if you search for your friend Joe and it pulls up a photo of your friend Josephine, maybe that's not a big deal because the cost of an error is not that high. In a different scenario where you're trying to detect insurance fraud or something like this, and you're directly sending someone to court because of some machine learning model output, then the errors make a lot more sense to be careful about. You want to be very thoughtful about how those errors translate to downstream effects. The same is true in BCI. So, for example, if you're building a model that's decoding a velocity output from the brain versus an output where you're trying to modulate the left click, for example, these have sort of different trade-offs of how precise you need to be before it becomes useful to the end user. For velocity, it's okay to be on average correct because the output of the model is integrated through time. So if the user's trying to click at position A and they're currently at position B, they're trying to navigate over time to get between those 2 points. And as long as the output of the model is on average correct, they can sort of steer it through time with the user control loop in the mix. They can get to the point they want to get to. The same is not true of a click. For a click, you're performing it almost instantly at the scale of neurons firing. And so you want to be very sure that that click is correct, because a false click can be very destructive to the user. They might accidentally close the tab that they're trying to do something in and lose all their progress. They might accidentally hit some send button on some text that is only like half composed and reads funny after. So there's different sort of cost functions associated with errors in this space. And part of the UX design is understanding how to build a solution that is, when it's wrong, still useful to the end user.
That's so fascinating, that assigning cost to every action when an error occurs. So every action, if an error occurs, has a certain cost. And incorporating that into how you interpret the intention, mapping it to the action, is really important. I didn't quite, until you said it, realize there's a cost to like sending the text early. It's like a very expensive cost.
It's super annoying. If you accidentally, if your cursor, imagine if your cursor misclicked every once in a while. That's like super obnoxious. And the worst part of it is, usually when the user's trying to click, they're also holding still because they're over the target they want to hit and they're getting ready to click, which means that in the data sets that we build, on average, it's the case that sort of low speeds or desire to hold still is correlated with when the user's attempting to click.
Wow, that is really fascinating.
It's also not the case, people think that, a click is a binary signal. This must be super easy to decode. Well, yes, it is, but the bar is so much higher for it to become a useful thing for the user. And there's ways to solve this. I mean, you can sort of take the comp-out approach of, well, let's just give let's take 5 seconds to click. Let's take a huge window of time so we can be very confident about the answer. Yeah. But again, world's best mouse. The world's best mouse doesn't take a second to click or 500 milliseconds to click. It takes 5 milliseconds to click or less. And so if you're aiming for that kind of high bar, then you really want to solve the underlying problem.